Learning Outcome 1-3. Determine memory, causality, stability, linearity, and time invariance, given an input-output definition of a system. This video is for the subproperty linearity. Linearity. The definition of the property linearity is: a system is linear if it satisfies the following two properties. 1. Additivity. If the response to x1 of t is y1 of t, and the response to x2 of t is y2 of t, then the response to x3 of t, which is the sum of x1 of t and x2 of t, is y3 of t, which is the sum of y1 of t plus y2 of t. 2. Homogeneity or scalability. If the response to x1 of t is y1 of t, then the response to x2 of t, which is a scaled version of x1 of t, is y2 of t, which is a scaled version of y1 of t, for any complex number a. Write these definitions in your notes. You're going to need them. Let's think about how this works. Let's first look at the subproperty additivity. Here we've got our system. Our input is x of t, our output is y of t. Again, this is an input-output definition of a system. Look at the letters x, look at the letter y. If we call our input x1, the output will be y1. If we call our input x2, our output will be y2. And for additivity, we're looking at an x3 producing a y3, where x3 is the sum of x1 and x2, therefore y3 will be the sum of y1 and y2. We need to go through the algebra to show whether or not this holds, given a definition of how y is related to x. For the subproperty homogeneity or scalability, here we're looking at our system, again with our x's and y's, but now our x2, which produces our y2, is a scaled version of this original x1, and that needs to produce a y2, which is a scaled version of the y1, the same scale factor a. Let's try an example. Here's an input-output definition of a system. Y of t is 2x of t. We want to know whether the system is linear or not. We're going to look at our x's and our y's. We have to have our x1, x2, x3 producing our y1, y2, y3. And that x3 has to be the sum of x1 and x2, producing a y3, which is the sum of y1 and y2. Then we have to do the work for scalability, where we only need to worry about x1 and x2, producing y1 and y2. And here, x2 is a scaled version of x1, y2 is a scaled version of y2. But we're going to take that and now make it concrete by defining how y is related to x. And that's going to, same thing's going to hold, that same equation's going to hold for y1, and we need to show that if these are defined, that we get the same relationship for our x2 and our y2. So let's work out this example. Additivity. We'll start with additivity. We start by defining our systems y1, y2, and y3 in terms of x1, x2, and x3. This is just our original system definition, our input-output system definition, for signals 1, 2, and 3. We just write them out. Then going back to the definition of linearity and additivity, x3 has to be the sum of x1 and x2. So we state that. Then we're going to do some algebra by taking this x3, we're going to substituting it in to the x3 above. This is just algebra. We continue and do more algebra, just simplifying things. I strongly encourage you to use these extra square brackets when you make that substitution in that fifth line. That keeps you everything nice and neat and tidy, so you can keep track of what you're doing, and I can keep track of what you're doing. While it's not a significant amount of algebra between lines 5 and line 6, I want you to show it. This first term we've seen before, up at the very beginning, we know that that's y1, so we can then substitute that as being y1. This second term we saw up at the beginning is just y2. So we can say that that is y2. And since this is what we were looking for, we can put a check mark and say additivity is satisfied. This is all the work you need to show for additivity, and I want you to show all of it, again including these algebra steps which look pretty obvious. I know that they're obvious to you. I hope that they're obvious to you. Please show them anyways. This is part of showing your complete work. Next, let's try scalability. For scalability, we need to define two system definitions, x1, x2, y1, y2. And then we need to define that x2 is a scaled version of x1. Similar to its additivity, we're now going to take this and substitute it in to the previous line. Again, please show those square brackets so we see what you're substituting in. Next is some algebra. Please show multiple steps of algebra, even if you think it's obvious. If you don't show your work, you don't get credit. And when we do this algebra, rearranging things, we again get this form of 2x1, which we saw up above is y1. So we want to do the algebra to rearrange things to get it in a form of our y1. We can then substitute in the y1, and we get the same scaled factor that we had when we defined our x. If x2 is a scaled version of x1, y2 is a scaled version of y1, therefore scalability is satisfied. Sounds pretty good. We satisfied additivity, we satisfied scalability, but the original question was, is this system linear? Well, the system is linear because both additivity and scalability are satisfied. So you need to state that next. You need to show all this work for scalability, the previous work for additivity, and then make the final statement that the system is or is not linear. In this case, it is linear. Let's try another example. Y equals x squared of t. You might have some intuition about whether or not this is linear based on your past courses. But you cannot just simply state, yes it is or no it is not. You need to go through and show all the work. So is this system linear? Start again with additivity. Please pause the video and write the first 3 steps for additivity. They'll be the same 3 steps that you wrote for example 1, but with a new system definition. Refer back to your notes. I hope you're taking notes of what you saw, or rewind the video and figure out what those first 3 steps are. I hope you got these first 3 steps. Again, it's just defining y1, y2, and y3 in terms of x1, x2, x3 using the definition of the system that was provided. What comes next? We're looking at additivity, which is saying that x3 is the sum of x1 and x2. So we state that. What's after this? Now we're going to substitute our x3 into the previous line. Again, please use extra brackets and show your work. Next is some algebra. Some more algebra, but now we can substitute in saying that this x1 squared we saw before was our y1, and that our x2 squared is our y2. And then we have some other stuff left over because that does not have an equivalence to y1 or y2. Because y3 is not just the sum of y1 and y2, we wind up with a not equals, which is different than the previous example. In the previous example, we got an equality. We put a check mark and said additivity was satisfied. When we do not get an equality, we put an X mark and say additivity is not satisfied. If we're trying to determine linearity, we have to have both additivity and scalability satisfied. If additivity is not satisfied, then we know that we cannot have both satisfied. And we can stop here and say that because additivity is not satisfied, the system is not linear because additivity and scalability are not both satisfied. You may stop here, you'll get full credit on your work. I'm going to go on and show scalability also, so you know how a negative case of scalability looks. Sometimes additivity will be satisfied, but scalability will not. So I want you to see the other example as well. For scalability, please pause the video and write the first two steps for scalability. These again will be very similar to the first two steps in example 1 for scalability. Look at your notes or rewind the video. I hope these are the first two steps you got. We're redefining the system now for the specific input x1 and specific input x2 using our system definition that was provided. What comes next? Remember, we're looking at scalability. We need to be able to scale our inputs and show that we get a scaled output. So we're going to scale our input and hope that we can get the scaled output. Next is algebra. We're substituting that x2 into the previous line. Again, please use lots of brackets and show your work. Algebra comes next. And we're trying to rearrange things so that we get things that look like our original function. And we're trying to get a scaled y1. But we didn't get just a scaled y1, so again we failed in our attempt. So instead of a check mark, we put an X. Scalability is not satisfied. And we can now state the system is not linear because additivity and scalability are not both satisfied. Now you've done two examples. Future problems look very similar to this, just with a different system definition. It'll either be positive or negative, as far as whether you're able to satisfy additivity and scalability. Look through these steps. The sequence always is the same. The trick is to always show your work.